life cycle assessment for the hot in place and cold in place for the Federal Highway Administration. So the way this works, you preheat this. Usually you have 2 or 3 vehicles. You can see you have a lot of heat there. And then you start the recycling process here. This is the scarifiers, and then you placement, this one placement, the hot mix asphalt, and then you start the compaction process. So this one, it can reduce the greenhouse gases between 20 to 60 based on the projects and the level of traffic that we were dealing with in the projects that we looked at. So this is really great. The most important thing is we need to make sure that a technique like this will give us the appropriate service life and the appropriate performance, because if it's not, you're going to be losing all these kind of advantages that you have. So one of the things we were looking at is to try to mill and put an overlay. Now the difference here is that when you put an overlay and you do hot in place, you don't have transportation here for the hot in place. You have all the materials in place, while this one here, you're going to take this material, send it to the plant, then recycle it, and then bring it back and put still an overlay. So you can find that there is some really good difference between the two. The most important thing here that you can find that when I look at the whole thing together, I couldn't see that big of a difference here in the energy. I could see here a change, of course, when I look into the change in the transportation, how I'm bringing the materials in. So what I'm trying to say with this example here is things cannot be sometimes accurate as it appears. So even if you have 100% cycling, that doesn't mean that this is the case and this is a good example. And I can tell you one of the things that we looked at is one of the plants they have acquired in their plant, and maybe that plant is not as efficient, and there is a good state-of-the-art plant somewhere else, but they have to transport a lot of the materials to that plant. So in that case, when you start calculating everything, that will maybe change our view. So another thing which is really interesting, and this is closer to my heart, which is the use phase. The use phase is mainly trying to look at 3 things. One is the rolling resistance, and this one here I'm going to elaborate more on it because it's really important, and this is a very challenging topic. The second is to look into the albedo. Now, a lot of people think that if this is a whiter surface, this means it's going to be better, and so on. I'm not debating these issues here, but I can tell you the albedo is a little more than this. Then we get into the lighting, and I'm going to go back and spend a few times here. Let's look into a truck driving on a road. This truck, if driving at 60 miles an hour, we'll find that the aerodynamic drags consumes about 40% of the fuel, and that's what we refer to as the aerodynamic drag. Then you have the mechanical losses, which is maybe approximately 25% of the fuel. Then you get 35% of the fuel, it's based on the rolling resistance. And that's where the idea of using white base came about. Using a white base tire will definitely reduce the amount of fuel. If you are reducing the amount of fuel because of the reduction in the rolling resistance, then that you are reducing the emission. But if we're going to be looking at this advantage, there is another thing that we need to look at it. Does this put more stresses, or does this going to cause more problem into the pavements? So one of the things that we are currently looking at is looking into the rolling resistance. The rolling resistance is the energy dissipated by a tire per unit distance covered. In order to do that, there is 3 different parts. The first one is the texture, the second is the roughness, and the third one is the structure. So, and this is the one that we are working more on. So if we look into the pavement-tire interaction, we have several parameters that we're going to look at. First, the pavement characteristics. Second is the tire type and size. And third is the vehicle type and load, and the axle configuration. And of course, we have the environmental conditions. So all this will affect the riding equality. And if you have a bad riding quality, you're going to have an increase in the stresses, increase in the energy and fuel force consumptions, increase in the tire tear and wear, and increase in the vehicle damage, and increase in the brake damage. So all this now is going to be affected by the riding equality. There is, for the picture, there is a very simple model that it was developed by or it's the HDM4 model, which is originally developed by the World Bank. And this model is very simple here, related the picture that we have related to the speed, and based on that you can calculate the fuel consumption. This is very simple, but what we can do is to calculate this based on the mean profile length. The second one is to look into the roughness. The roughness can be done in a very simple way, or more complicated way. The simplest way is to look into the IRI progression model, which we developed, and this one is on real data. It has to do with the thickness of the pavement, as well as the original IRI, and the equivalent single axle load that we have. Then, we look into the IRI over time. The IRI over time increase, which is the roughness, that's the International Roughness Index. It's increased with time, and every time you have a rehabilitation, it will go down and it will go up and so on. And that depends on what kind of pavements we are dealing with. So they developed some models, and these models based on the HDM4, it's very simple, which is just looking into a relationship between the energy and the speed, and as you can see here, and the IRI, and looking at this at different speeds, and you can be using some of the existing models to do that, such as the one in Moose. The way that we looked at it is took it a little different here, where we are trying to look at this from the other perspective, which is the energy and the emission, and see how this now is affecting the energy coming from the cars, as well as the produced emission. But the most important part of what we are doing, which is the more, I guess, in my opinion, very meaningful going to be, is the impact that we are getting from the structure itself. And before I go through this here, I wanted to add an important point, that we spend a lot of time on understanding the interaction between the pavement and the tire. But we need also to know that most of the issues are with the tire itself, because the tire is much more deformable, and it's going to be affecting almost 90% of all the rolling resistance. So looking at the pavement is very important, but also looking at the tire is really important. So we're working with Michelin, and we're developing now models for the tire itself. So first we designed the tire, or we simulated the tire, we collected the materials properties of the tire, and we have very, very good simulation of the tire. These simulation of the tires were calibrated or correlated to real measurements were done at different loads and different tire pressures in South Africa using pads that it has more than 1,000 sensors. So that will allow us to have a very good idea about the contact stresses that we're getting, and we use that to validate the model that we have. So we're not talking about the model itself, but we're going to be talking about the structural rolling resistance. In order to do this in an accurate way, and at the same time, the least computing time, we came up with three steps. The first step here is to look into a simplified pavement, where we have the model of the tire itself, where we have this as a hyperelastic, and we apply this into an elastic, rigid pavement. From this, we get the contact stresses. We take the contact stresses. Over the years, we have been developing I would say, we spend a lot of time over the years to develop a very good modeling for the pavement itself. So, the material here has a viscoelastic for the asphalt concrete, has an anisotropic for the granule material and subgrade. We take the contact stresses that we measure here, and we put it here. So now we have the response. The problem with this, which is good, is that it's very time consuming. So what we did, we took the measurements from here, and we put the boundaries, and the measurements that we got there, we go ahead and coupled it together, and we can now have this as the viscoelastic, and we have now the tire itself, and that will be less time for the computation that we're dealing with, so that will give us a very detailed tire roll over from that, we look into now what we can get from a model here that it has to do with the load and the pressure and the temperature and the velocity. This is here the model based on real data, and we correlate that of what we are getting from the finite element, and you can see that we have some really good prediction from the finite element compared to the model that we got from real data. Now, we can look at this also from 2 points. One is to look at into the dissipated base structural rolling resistance, or look at this in a very simplified way, which is as an output from the finite element, which is the deflection-based structural rolling resistance. So if we look at this one, this is going to be more time-consuming and more extensive. This one is the data that we're getting from the nodes on the surface, and we will be able to get these nodes, deflection nodes, based on the contact stresses and the forces that we are applying on the nodes, sorry, forces applied on the nodes. We can get this information, and we use this information in order to calculate the rolling resistance. Now, we did both to see if there is any difference, of course, because this one is time-consuming. This one here is very simple, and the data is already as part of the outcome, and you see that the difference is very, very minimal. So I think I'm good on time. I'll spend just another 5 minutes or so telling you about the project that currently is going on. This project is to develop the first regional tool based on regional data for the tollway. This is a big project that is involving the life cycle assessment for pavements, for drainage, for structures, including bridges, for lighting, and for the landscape. There is colleagues from industry working on this tree. One of my colleagues is working on the drainage also, and we developed one for the LCA. So I'm going to talk about the pavement LCA. So I'm going to show you here how the tool and the capability of the tool. So the tool is simply, you have input data, and you have the 5 phases that I talked about, and you can choose which phase to include, which is the one that you don't want to include. So it's very detailed, and again, the life cycle is all about data and good data and accurate data. So we try to collect as much data from the area as possible. Whatever it's not, we'll go to the existing databases. So this is here the general characteristics about the pavement, and the information about the pavements and so on. So this is just general information about it. Then we go to what kind of materials it's used, and we have all the characteristics that it's needed in the materials in the database or you provide. Then you choose what equipment. Just by selecting the equipment that it's used for any of the processes, all the information about the emission, the energy becomes available. It's part of the database. Then you need to provide, of course, the travel distance and so on, because that's going to be important. Then the mix design, and that's what you are telling us, what kind of materials you are putting in this mixes. One of the things that I wanted to mention, which is very important, is the pay factor. When we are designing a pavement, we're always dealing with different layers and so on. Here, we have to do it in a completely different way. We have to do it based on the pay factor, because if you go to the Department of Transportation or you're talking to a contractor, they're always providing you with the information based on a pay factor. So everything here is based on the pay factor. It has a number, and anything you choose from here, you'll find all the information about the energy and the emission and so on. If it's not here, you need to add it. Okay? So I think just for the pavement part, we have more than maybe 400, 500 systems. So the maintenance phase, this is including the snow removal, repair, crack sealing, whatever. So all this information, and again, the associated energy and the details about the components, energy as well as the emission are there. And then you go to the use phase, and the use phase including the rolling resistance, the albedo of this. One of the things about the rolling resistance that I was talking to some of your colleagues this morning, that we also we are concerned about like the tollway. The reason why you pay money for the tollway is that you do not have any delays. So we have to take into consideration the congestions, the change in the speed, and all these variations in the speed of the traffic during the work zone in the work zone area. This is all part of the modeling. The change in the speed during that process, it's all part of the modeling that will give us the emission and the energy also. So the use phase is the one that it took us the longest too. And of course, the end of the life, you decide how much of that's going to go for a landfill, or it's going to be recycled on site, or go back to the plant, and so on. So at the end, you will get the data in many different ways. What is the impact of CO2, greenhouse gases, the global warming? In any form you want it, you can get the data. So I'm going to go quickly here showing you two projects, one built in 2011, one in 2015, and one it has a CMA over jointed plain concrete and full depth hot mix asphalt winding. The other one, it has CMA, but it's continuously reinforced. The design life for this one, the jointed was 22, that one was 30. Of course, they have different length, but always we look into just a functional unit, which is 1 mile. In this case, they have different traffic expected on both. So the intention here is not to compare them, by the way. The intention is just to show you that they can be different. So the global warming, you can see here for this particular one, the first one, you have more in the use phase. Less in the use phase. This one has much more impact from the use phase because there is more traffic is used on that one. And you can see for the total primary energy here that the feedstock of the binder is part of it. So that's why it's going to be a little different. So you can see also here the difference between the different phases, the material and construction as one, the maintenance and the use phase at the end of life. So you will be able to look at each one of the project. If you look at the results here, we can look into the global warming, and you can see here the difference between this one and this one. So this one here, it's going to give you a higher life, which was 30 years, this is 22, but also less global warming, less primary energy, less fuel, less single source. The single source is looking into 10 of the parameters that's impacting the environment, such as CO2 and so on, and the percent cost. So in a way, if I'm going to look at this here, I can say that the DOT or the tollway has been doing something to improve their sustainability over the past 4 years. What we are doing right now, we're looking into 10 projects, and these 10 projects look at it over 15 to 10 years and see what they have done. This can be through using recycled materials. This could be used. This could be due to a change in the design. All that is part of the sustainability. So finally, I want to say here that the future of flexible pavement sustainability requires that we start to develop and utilize quantitative and holistic and systematic approaches. And I think that in the next 5 years or so, we will be seeing life cycle assessment start to be implemented and part of the contracting process. Using recycled asphalt binder has been shown to quantitatively reduce environmental burdens under one condition, when the performance is working very well. But at the same time, we need to take everything back to the origin and see what is going to be the impact. Now, of course, it's not part of what I wanted to discuss today, but always when you go back, if we are producing asphalt, for example, at a refinery, the energy that you spend to produce the asphalt, how much is going to go to the asphalt, how much is going to the gasoline, kerosene, these things where we're going to have rules, and these rules are being developed, and these rules will be adopted by everybody, and that's why it's very important, so everybody can, so you will not have double dipping. That's what I was trying to say. And the use phase is complex component of the LCA, and rolling resistance is definitely the one that it has the greatest impact on the environment, and we definitely need to work more in this field. The texture and the albedo is maybe not that complicated, but definitely the rolling resistance it's a big field, and that's something that we have been working quite a bit actually on it. But we're not working on it from the pavement's point of view, we're working on both, because as I said, I do believe that a lot has to do with the tire than the pavement itself. So we need to focus on the tire, and that's what we have been doing for the past 20 So we definitely need to develop tools to perform the streamlined life cycle assessment for paper. So with that, I would like to acknowledge the different organizations that have been working with us and supporting this research, and I'll be more than happy to take any questions. So thank you so much.
Okay, thank you. Any questions?
No, I have a question.
Yes, please.
In the life cycle analysis, I think a lot of the time this is getting, the model itself or the process, how did you prevent double counting?
Excellent.
Because a lot of times there's an issue there.
Excellent. So there is many ways to, the double counting actually, it's not an issue when we're talking about transportation, when we're talking about the materials that we're getting. The double counting, it becomes when we are dealing with, let's say, the asphalt binder or the recycling. For example, when I recycled my material, shall I kind of claim everything during the recycle for the new project, or this is part of the previous project? So there's many different approaches to do that. There's some that they are detailed, or some, which I think that's where they're gonna go, which they call it the split approach, where they're gonna say, if you are recycling this material here, you can claim 30 at the end of the life, and 50 at the end of the life, and 50 for the people who are doing the recycling and put it in the new materials. Because if you're going to take this recycled material and you put it in your mixes, you need to have some kind of energy was spent on that. So you don't want to just say, I'm going to be claiming everything. You cannot do that because the other person who used it before, maybe he claimed or she claimed everything. So what we do is that's where we are creating